Okay, so this is the fifth lecture in chapter 5, and I am still talking about mass balance. Now I want to solve a third example. So this is a third example about mass balance that I want to discuss. I want to read the example with you and sketch the diagram so that we can solve it later. So let me read it and sketch it with you. Okay. So a well-stirred storage vessel contains 10,000 kilograms of solution of dilute methanol. So I have a well-stirred. So I have this is a storage vessel. Well-stirred means there is a mixer or agitator here, and this one contains 10,000 kilograms of solution. So inside there is 10,000 kilograms of what? Methanol solution. So methanol solution. Okay, methanol solution. And the mass fraction of alcohol is 0.05 0.05 or 5%. So WA is equal to 0.05 WA. So there is 5% of methanol out of this 10,000 kilograms. A constant flow of 500 kilograms per minute of pure water is suddenly introduced. So now there is here 500 kilograms per minute of H2O, of water, into the tank, and a constant rate of withdrawal of 500 kilograms per minute of solution started as well. So I am withdrawing again 500 kilograms per minute of solution. So this is a dilution process. So there was methanol solution in the tank at the beginning. So methanol solution, it is well mixed. Then there is this agitator or mixer. Then I am inputting here, as you can see, 500 kilograms per minute of water. I am diluting it, and I am withdrawing the solution, and the concentration of the solution is just going to change. It's going to change with time. Okay, it's going to change with time. So I can say that the concentration here is WA, and this is constant. I mean, this is the start. This is where we started the concentration at the beginning. Okay, so this is at t equal to 0, let us say. So he's asking then to what? Calculate the time for the alcohol content to drop to 1% by weight, 1%. So I started with 5%. I want the time so that this 5% will drop to 1%. Okay, so this is the summary of a problem, as you can see, where we have the 500 kilograms per minute of H2O. We have to start with 10,000 kilograms of solution, 5% methanol, and we are withdrawing 500 kilograms per minute of the solution, and we're asking for the time that this concentration will drop from 5% to 1%. So first of all, we have to think about the assumptions. The first thing is water is incompressible. Actually, all the solutions here, methanol, water, the mixture is incompressible. Second thing is there is no reaction, so there is no generation, no consumption, and we can say that the volume will not change when those, let us say, water and methanol are mixed, and it is well mixed as we have this mixer here, so the density will not change. Okay, so from where to start? As usual, well, let's start from the conservation of mass equation. So I will say dmCV dt equals mn minus m out. So this is like the overall mass balance. So dmCV dt is equal, so how much mass is going in is 500. So I have 500. How much mass is going out is 500. So 500. So I am getting then this is equal to 0. So dm cv dt equal to 0, which means that mCV is equal to a constant, because there is no change. The change in the mass in the control volume is equal to 0, which means mCV is constant. And actually, this is obvious, since 500 is going in, 500 is going out. So we know that what is inside the, let us say, our control volume, if this is my, let us say, control volume, is 10,000. So from here, then I can conclude the following: mCV is equal to 10,000 kilograms. Okay, but this didn't tell me much to answer the question. I mean, he's asking for concentration as a function of time. Okay, concentration as a function of time. So this is just telling me that the mass in my control volume is not going to change. So what to do then? This is the overall mass balance. So it seems that I have to apply the component mass balance. Component mass balance. So which component I'm going to apply here? The mass balance on is the methanol. Okay, so again I will write the same, let us say the same equation. So I will say dmCV dt equals mn minus m out. Okay, but now I'm talking about methanol. I'm not talking about, for example, the solution. I'm just talking about methanol. So I have to change this equation into, let us say, equation for methanol. So ddt, and now it is what? It is the, let us say, the mass in the control volume m times the concentration of methanol in the control volume is equal to how much mass is going in, which is total. So I will just say mn times the concentration of methanol in the input stream minus mass going out times the concentration of, let us say, Wn, and this is W out, because I am just considering the methanol component here, methanol mass balance. I can use the product rule here. Okay, so this will be what? This will be equal to m dW dt plus W dm dt equals what? Mn times Wn. So what is the concentration of methanol going in? There is no methanol in the input stream, it's just water. So this is 0 minus, what is m out? It is 500. Okay, 500. And this is the concentration of methanol in the output stream, which I don't know because it is changing with time. I am adding water and this is changing. So I will just say it is W. This is the concentration inside the tank. This is the concentration in the output stream. But they are the same because I am taking this, let us say, methanol from the tank, and the tank is well mixed. So the concentration here is the same as the concentration here. Okay, so I will just call it W, which is equal to W out, or W, which is the concentration of methanol. Okay, so what else? We can look at this again. We can look at this thing here, but dm dt is equal to 0 because there is no change of mass in the control volume. Okay, there is no change of mass in the control volume, so also I can just set this equal to 0. And for m, we know that m, we just found it from the first part to be equal to 10,000. So I can write this as 10,000 dW dt is equal to minus 500 W. Okay. Okay, so we reached this equation. Now I can just cancel this, the 2 zeros with these 2 zeros, 5 with 100, so I will get 20 here. So I am getting what? I'm getting 20 dW dt equals minus W. Okay, I can rearrange this equation. So I'm going to get what? I'm going to get dW over W is equal to, so I will take this the other side, 1 over 20 dt. Next step is to integrate. So I will integrate both sides. Usually T we start from 0. When the concentration 0, the concentration here in the tank was 5%. Okay, and then the concentration dropped to 0.01. That's what he's asking for. What's the time required? What the time required so that the concentration will drop from 5% to 1%. So this is an easy integration to solve. This is ln W from 0.05 to 0.01, and this is equal, this is an easy integral, T over 20. Okay, so what's this? So this is ln 0.01 over 0.05 equal to T over 20, and then solve for T. Okay. Okay, so sorry, actually I forgot the negative sign. So there's a negative sign here, there's a negative sign here, there is a negative sign here. And when you solve for t, you will get t is equal to around 32 minutes, I believe. Okay, so this is the solution. It will take 32 minutes for this tank, or for the concentration of methanol in the tank to drop from 5% methanol to 1% methanol.